Standing in the shadow of the Great Pyramid of Giza, or gazing up at the massive stones of Stonehenge, it's impossible not to feel a sense of awe and a burning question. How did ancient civilizations, without the benefit of modern machinery or advanced technology, accomplish what seems nearly impossible even by today's standards? The answer might lie not in the monuments themselves, but in the forgotten tools that built them. Across the globe, buried in the dust of time, are clues, artifacts that hint at techniques and knowledge lost to history. These aren't just simple hammers or chisels. They're pieces of a puzzle that challenge everything we think we know about ancient engineering. Take a moment to picture the precision of the pyramid's alignment with the stars, or the way massive stone blocks at Saxehuaman fit together so tightly you can't slip a sheet of paper between them. These aren't accidents. They're the result of tools and methods that, in some cases, we still don't fully understand. Some of these tools seem rudimentary at first glance: copper chisels, stone spheres, weighted strings, but when you look closer, they reveal an ingenuity that borders on the unbelievable. How did copper, a relatively soft metal, carve through granite? How did ancient builders drill perfect holes into solid rock? And why do some of these tools suggest a level of mechanical sophistication that textbooks claim didn't exist for thousands of years? This is where history gets thrilling, because every one of these tools tells a story, not just of how something was built, but of the minds behind it. The people who crafted these tools weren't just laborers. They were innovators, problem solvers, perhaps even geniuses whose names we'll never know. Today, we're going to uncover 23 of these forgotten instruments, each one a window into a world where the impossible was just another day's work. By the time we're done, you won't just see ancient monuments differently, you'll see human history in a whole new light. So let's begin this journey together, piece by piece, tool by tool, unraveling the mysteries of the past. Copper chisels from ancient Egypt present us with one of history's most fascinating contradictions. At first glance, they appear hopelessly mismatched for their task: soft copper against unyielding granite or basalt. Yet these very tools shaped some of the most enduring monuments ever built. The secret lies not in the copper alone, but in the ingenuity of the craftsmen who wielded them. Modern experiments reveal that when paired with abrasives like quartz sand, copper chisels could slowly grind through even the hardest stone. Picture a team of workers patiently guiding these tools, the sand acting like microscopic teeth, gradually carving precise lines over weeks or months. But here's where the mystery deepens. Some cuts in ancient stonework are so clean, so exact, that researchers debate whether simple abrasion alone could account for them. Could the Egyptians have possessed a lost method for hardening copper beyond what we understand today? Ancient texts mention treatments involving heat and mysterious compounds, descriptions that modern metallurgists struggle to replicate. One theory suggests they might have used a form of work hardening, repeatedly hammering and annealing the copper to increase its durability. Another proposes the use of natural alloys or coatings that have since eroded away. Then there's the tantalizing possibility of an entirely different technique, perhaps a chemical process or even a forgotten tool used in tandem with the chisels. What makes this puzzle even more compelling is the sheer scale of the work. The Great Pyramid alone contains over 2 million stone blocks, many precisely shaped with these rudimentary-seeming tools. The patience and skill required are almost unimaginable by today's standards. Yet, the precision speaks for itself. Angles cut so accurately that they align flawlessly, surfaces smooth to near perfection. Whether through lost knowledge, relentless patience, or a combination of both, the copper chisels of Egypt stand as a testament to what human hands can achieve. And they leave us wondering what other secrets of ancient craftsmanship are still waiting to be uncovered. High in the Andes, nestled near the imposing walls of Saxehuaman, lie strange spherical stones that defy simple explanation. These aren't just decorative artifacts, they're tools, and their design reveals a startling level of sophistication. Each stone, carefully carved with deep grooves, fits snugly into the palm of your hand. At first glance, they might resemble oversized marbles, but their true purpose becomes clear when you see the evidence left behind. The ancient builders of Peru used these spheres as drills, spinning them with cords to bore perfectly circular holes into solid rock. Imagine wrapping a cord around the grooves of one of these stones, then pulling it back and forth like a yo-yo. The motion would set the sphere spinning at high speed, its surface grinding against the stone beneath it. With the addition of sand or water as an abrasive, the drill could chew through even the toughest granite. What's remarkable isn't just the method, it's the precision. Some of the holes found at ancient sites are so uniform, so flawlessly cylindrical, that they rival what modern machinery can produce. This raises a fascinating question. How did ancient cultures develop such an advanced understanding of rotational force? The physics behind these drills, converting linear motion into smooth, sustained rotation, is a principle we associate with much later inventions like the potter's wheel or even early engines. Yet here in pre-Columbian Peru, builders were applying it with masterful skill. Some researchers speculate that these drills might have been part of a larger, more complex toolkit, possibly used in ways we haven't yet uncovered. Even more intriguing is the possibility that these spheres weren't just standalone tools. At sites like Ollantaytambo, you can find rows of precisely drilled holes that seem to serve no obvious structural purpose. Were they part of an anchoring system, a method for testing stone quality, or perhaps something more enigmatic like a form of ancient surveying? The stones themselves hold clues. Some show where patterns suggesting they were used for extended periods, while others appear almost pristine, as if they were part of a specialized set. What makes these drills truly extraordinary is the way they challenge our assumptions about technological progress. We often picture ancient tools as crude or simplistic, but the stone sphere drills of Peru prove otherwise. They represent a marriage of practicality and ingenuity, a solution so elegant that it still inspires engineers today. And they leave us wondering if something as seemingly simple as a spinning stone could achieve such precision. What other forgotten technologies might have been lost to time? The Diabass pounders of Egypt present a paradox: massive, fist-sized stones that seem almost primitive at first glance, yet were instrumental in creating some of the most refined sculptures and obelisks in history. Carved from dense volcanic rock, these pounders could weigh as much as 10 pounds each, and their surfaces often show clear signs of wear from relentless striking. The process seems straightforward. Workers would have pounded away at softer stones like limestone or sandstone, gradually shaping them by brute force. But when you examine the results, the razor-sharp edges of an obelisk or the smooth curves of a statue's face, the story becomes far more complicated. How could such heavy, blunt tools achieve such delicate precision? One theory suggests that the pounders weren't used alone. Ancient artisans might have employed a multi-stage process, starting with these rough tools to remove bulk material before switching to finer abrasives or even copper chisels for detail work. But some carvings show no evidence of transitional tools, just the unmistakable pockmarks of Diabass pounding leading directly to a polished finish. This has led researchers to speculate about lost techniques, perhaps a method of controlled fracturing or a chemical treatment that softened the stone temporarily, making it easier to shape. Then there's the question of scale. The unfinished obelisk at Aswan, still lying in its quarry, offers a rare glimpse into the process. Weighing nearly 1,200 tons, it was partially carved using these pounders before a crack halted production. The sheer labor involved is staggering, thousands of hours of pounding by teams of workers. Yet, the surfaces that were completed are eerily flat, with angles so precise they suggest a system of measurement or guidance beyond simple hand-eye coordination. Some researchers point to faint grooves and markings near these sites, possibly remnants of wooden templates or string lines used to maintain accuracy. But the most tantalizing possibility is that the pounders were part of a larger, lost system. A few surviving reliefs show workers using what appear to be tools with handles, possibly mechanical aids that amplified force or improved control. Could there have been a form of ancient power tool, leveraging leverage or even water pressure to assist in the shaping? The absence of such devices in the archaeological record doesn't rule them out. Many materials, like wood or leather, wouldn't have survived millennia. What remains undeniable is the skill of the craftsmen who wielded these stones, turning raw rock into monuments that still awe us today. Their work whispers of knowledge we've yet to fully decipher, leaving us to wonder what other secrets are hidden in the dents and grooves of these unassuming tools. The Roman Groma seems deceptively simple, a wooden cross with plums hanging from each arm, mounted atop a sturdy staff. Yet this unassuming tool laid the foundation for one of history's most precise building traditions. Picture a surveyor standing at the center of a future road, rotating the Groma until its weighted strings aligned perfectly with the cardinal directions. The Plumbobs acted as living guides, their stillness confirming true verticality even on uneven ground. With this humble device, the Romans plotted straight roads stretching hundreds of miles and erected temples with near mathematical perfection. But when you stand beneath the Pantheon's dome, its oculus perfectly framing the midday sun on the equinox, questions arise. The Groma's margin of error, though small, shouldn't account for such celestial precision across vast structures. Some researchers propose supplemental tools, perhaps mirrored surfaces to catch sunlight or water-filled trenches, acting as natural levels used in tandem with the Groma. Others point to the Romans' mastery of geometry. They might have employed ropes knotted at precise intervals to create improvised measuring grids, combining multiple Groma readings for flawless alignment. What's often overlooked is the Groma's versatility. Beyond mere alignment, it enabled complex urban planning. Roman cities featured intersecting streets at perfect right angles, drainage systems with calculated gradients, and amphitheaters where every seat had an unobstructed view, all achievable because the Groma could measure both straight lines and precise angles. Modern reconstructions prove its effectiveness, yet when used alone, even expert surveyors struggle to match the precision of ancient sites. This gap hints at lost refinements. Historical accounts mention chorobates, a sophisticated leveling instrument, and dioptra, a sighting tool possibly used for long-distance measurements. Could these have complemented the Groma for critical projects? The Pantheon's dome, weighing over 5,000 tons, stays standing through exact weight distribution, a feat requiring measurements accurate to fractions of a degree. Whether through undiscovered tools or sheer human ingenuity, the Groma represents more than meets the eye. It's a symbol of how the Romans turned simple principles into architectural miracles, leaving us to ponder what other surveying secrets vanished with their empire. The Antikythera Mechanism shatters our assumptions about ancient technology. Recovered from a shipwreck off the Greek island of Antikythera in 1901, this corroded bronze artifact initially seemed unremarkable. until X-rays revealed its true nature. Inside its palm-sized casing lay a maze of interlocking gears, precisely calibrated to track celestial movements with astonishing accuracy. This wasn't just a calendar or simple clock. It could predict lunar eclipses, chart planetary positions, and even account for irregularities in the moon's orbit, a feat of engineering that wouldn't be matched for over 1,000 years. What makes this device so revolutionary isn't just its complexity, but what it implies about lost knowledge. The mechanism's differential gear, a component once thought invented in the 16th century, allowed it to perform calculations no handheld device should have been capable of in antiquity. The craftsmanship is equally staggering. Microscopic inscriptions guide the user through its functions, while nested gear trains operate with tolerances measured in fractions of a millimeter. This level of precision demands not just theoretical understanding, but generations of accumulated mechanical expertise. Now consider this: if the ancient Greeks could build such an intricate astronomical computer, what stopped them from applying similar principles to construction? The same gear systems that modeled celestial mechanics could have been scaled up to lift heavy stones or align monumental architecture. Some researchers speculate about lost machine shops in Alexandria or Syracuse, where such technologies might have been adapted for larger projects. While no direct evidence survives, the Antikythera mechanism proves the conceptual framework existed. The device's purpose remains debated. Was it a philosopher's teaching tool, a navigational aid, or perhaps part of a grander system? Its discovery among luxury goods suggests it wasn't unique, likely one of many advanced devices that simply didn't survive the ravages of time. This raises a haunting possibility. What if the mechanism represents not the pinnacle of ancient engineering, but a surviving fragment of a much broader technological tradition? The Romans wrote of automated theaters and mechanical servants. Might these have been real, using the same principles on a grander scale? Most tantalizing is the mechanism's connection to architecture. Its ability to predict eclipses implies knowledge that could have guided temple alignments, while its gear ratios demonstrate mathematical sophistication visible in Greek proportional systems. When you stand before the Parthenon's columns, their subtle curvature calculated to counteract optical illusions, it's hard not to wonder, was this the work of master builders alone, or did they have mechanical aids now lost to history? The Antikythera mechanism doesn't answer these questions, but it forces us to ask them. In doing so, it redefines what we thought possible in the ancient world. High among the mist-shrouded peaks of the Andes, the Inca star gauges sit silently, their weathered surfaces etched with angles so precise they seem to whisper secrets of the cosmos. These unassuming stone artifacts, found scattered near sacred sites like Machu Picchu, aren't mere decorations. They're celestial calculators, carved to measure the shifting positions of stars, sun, and moon. Picture a priest astronomer holding one of these gauges aloft at dawn, its notched edges framing the rising sun as it crests the mountains on the solstice. The alignment would be perfect, a moment frozen in stone, confirming the turning of seasons or the timing of sacred rituals. What makes these tools so extraordinary is their dual purpose. They're both practical instruments and profound spiritual symbols. Each angle corresponds to key astronomical events: the winter solstice sunrise, the zenith passage of the sun, or the helical rising of Venus. At Ollantaytambo, for example, a star gauge's 23-degree angle matches the sun's position during the June solstice, when sunlight would flood through a specially designed temple window to illuminate a ceremonial stone. But here's the mystery: some gauges feature angles with no obvious celestial correlation, leading researchers to speculate about lost constellations or even measurements for planetary cycles we've yet to decipher. The precision of these carvings defies simple explanation. Without metal tools, how did the Inca achieve such exact angles? Some gauges show where patterns suggesting they were used repeatedly, their edges smoothed by generations of hands adjusting them against the horizon. Others appear pristine, hinting at a master set kept for critical observations. The stone's placement is equally deliberate, clustered near water sources or atop ceremonial platforms, as if the act of measuring the heavens was intertwined with the life-giving forces of Earth. Debate lingers over whether the gauges were standalone tools or part of a larger system. At Coricancha, Cusco's Golden Temple, grooves in the walls align with star gauge notches, creating a kind of stone observatory where light and shadow would mark celestial events. Could there have been movable components, wooden inserts or cords now lost to time? Spanish chronicles mention Q-hippus knotted cords used for astronomical records, raising the possibility that the gauges worked in tandem with these devices to create a three-dimensional mapping system. Most compelling is the way these stones blur the line between science and spirituality. For the Inca, astronomy wasn't abstract. It dictated planting cycles, religious ceremonies, even the layout of cities. Machu Picchu's very orientation aligns with the Southern Cross, while its Intihuatana stone serves as a solar clock. The star gauges, then, weren't just tools but bridges between worlds, turning celestial patterns into tangible guides for daily life. Their legacy challenges us to see ancient technology not as primitive, but as a harmonious fusion of observation, craftsmanship, and cosmic reverence, a reminder that the sky above was once as much a blueprint as the earth below. The Egyptian Plumbob is one of those tools that seems almost too humble to explain the grandeur it helped create, a simple weight tied to a string, dangling gravity's truth. Yet, this unassuming device was the silent guardian of perfection in ancient construction, ensuring every block in the pyramids rose at a flawless right angle to the earth. Workers would have suspended these weights beside freshly placed stones, adjusting until the string ran parallel to the edge, confirming absolute verticality. It's a method still used today by masons and carpenters, a testament to its timeless reliability. But when you measure the Great Pyramid's corners against true north, with deviations of less than 1/10 of a degree, the Plumbob story grows more complicated. How did a tool with inherent limitations swaying in the wind, susceptible to human error, achieve such supernatural precision? Modern experiments show that even the steadiest hands using a traditional Plumbob can't consistently match the pyramid's accuracy. This gap has led researchers to propose a tantalizing theory. The Plumbob might have been just one piece of a more sophisticated system. Some wall carvings depict tools resembling frames with suspended weights, possibly early versions of the Merkhet, an astronomical alignment device. Could these have been used in tandem, creating a network of reference lines across the construction site? Others point to the Egyptians' mastery of water. Perhaps they used basin-filled trenches as liquid levels, creating perfectly flat surfaces over vast distances to cross-check their vertical measurements. Then there's the matter of scale. The pyramid's corners aren't just vertically true, they're geographically precise, aligned with the cardinal directions. A Plumbob can't explain this. It needs a reference to the stars or sun. Here, the Egyptians' dual expertise in astronomy and architecture may have converged. Imagine teams working at night, using the unchanging pole star to calibrate their tools, or marking shadows at equinox dawn to establish true east-west lines. The Plumbob would then become the earthly anchor to these celestial guides, a bridge between the cosmic and the practical. But the most compelling evidence of lost sophistication lies in the tool's evolution. Later Plumbobs discovered in archaeological sites feature grooves or notches, suggesting they were part of a larger apparatus possibly mounted on wooden frames or paired with sighting tools. One fragmentary text even mentions a golden thread plumb line, hinting at materials or techniques that enhanced accuracy beyond ordinary hemp and stone. Whether through refinement or complementary technologies, the Plumbob's role in pyramid construction challenges our perception of ancient toolkits. It wasn't just a weight on a string, it was the physical manifestation of an idea that human hands, guided by ingenuity, could bend stone to the unerring laws of the universe. And that idea, it seems, was sharper than we ever imagined. The Roman Volute lathe stands as a testament to ancient craftsmanship, a tool so precise it could transform solid marble into flowing spirals worthy of emperors. Picture a massive column slowly rotating as artisans guided their chisels along its length, carving the iconic scroll-like patterns seen in temples across the Roman world. These spirals weren't just decorative, they were mathematical marvels, their curves following strict proportional rules to create harmony in monumental spaces like the Pantheon or Trajan's Forum. What's astonishing isn't just the artistry but the mechanics behind it. Unlike simple pottery wheels, these lathes had to handle stone weighing tons, rotating smoothly enough to allow for millimeter-perfect carvings. Surviving examples of volute columns reveal clues that challenge conventional wisdom. Some spirals show tool marks with consistent depths and rhythms, suggesting a level of mechanical assistance beyond human strength alone. Historians debate whether these lathes were powered by treadmills, water wheels, or even counterweight systems, technologies the Romans certainly knew, given their aqueducts and cranes. A few fragmented reliefs depict what might be belt-driven mechanisms, hinting at an early form of continuous rotation. Then there's the matter of symmetry. Paired columns often mirror each other with near-identical spirals, implying the use of templates or guided systems to maintain uniformity across massive structures. The real mystery lies in the missing pieces. Roman texts mention machini for stoneworking, but details are frustratingly sparse. Could these have been geared devices, similar to the Antikythera Mechanism but scaled for construction? Some researchers point to Vitruvius's descriptions of cranes and hoists, wondering if the same principles were adapted for precision carving. Others speculate about lost apprenticeships, oral traditions where master craftsmen passed down techniques too valuable to commit to parchment. What's undeniable is the legacy of these tools. The volute lathe didn't just shape stone, it shaped an aesthetic language that defined an empire. Its spirals echoed in everything from triumphal arches to humble grave markers, a visual rhythm that still whispers of Rome's engineering prowess. And it leaves us with a provocative thought. If they could achieve such refinement with what we assume were primitive tools, what other mechanical secrets might have vanished when the workshops of antiquity fell silent? Buried in the sun-baked plains of Mesopotamia, the brick molds of ancient Sumer tell a story of mass production that feels startlingly modern. These rectangular wooden or clay frames weren't just tools. They were the backbone of an architectural revolution. Picture a riverbank workshop 4,000 years ago, where laborers packed wet clay into hundreds of identical molds, each producing a brick with precise dimensions. Once dried in the sun or fired in kilns, these uniform blocks stacked together like puzzle pieces, allowing ziggurats to rise with staggering speed. The Great Ziggurat of Ur, for instance, required an estimated 700,000 bricks, a number that would have been unthinkable without standardization. But here's what defies expectation. These molds weren't crude or haphazard. Archaeologists have found examples with wear patterns indicating they were used thousands of times, their edges reinforced with bitumen or woven reeds to resist warping. Even more impressive is the consistency bricks from the same period, found miles apart, often matched to within millimeters. This implies a level of centralized control we rarely associate with early civilizations. Were there royal inspectors checking brick quality, clay recipes guarded like state secrets, cuneiform tablets hint at brick accountants who tracked production quotas, suggesting an administrative system as advanced as the architecture it supported. The real mystery lies in the logistics. Constructing Ur's ziggurat would have required not just molds, but an entire ecosystem of labor: clay diggers, water carriers, kiln tenders, and bricklayers working in synchronized waves. Some bricks bear the stamps of specific kings or workshops, acting like ancient barcodes for quality control. Others incorporate straw or crushed pottery for added strength, revealing material science experiments lost to time. And then there are the bitumen-coated bricks, used to waterproof lower layers, a technique so effective that traces still remain after millennia of erosion. What's often overlooked is how these molds enabled more than just construction. They encoded cultural values. The ratio of a Mesopotamian brick's length to width, often 4:1, mirrors the proportions of their sacred altars and even cuneiform tablets. This wasn't random, it reflected a worldview where harmony in measurement echoed cosmic order. The molds themselves might have been considered sacred, their dimensions derived from celestial observations or divine decrees. Yet for all their sophistication, these tools raise unanswered questions. How did they maintain consistency across generations? Why do later Babylonian bricks show slight dimensional shifts, accidents of time, or intentional changes tied to astronomical cycles? And most intriguingly, could these molds have been part of a larger, lost system? Some ziggurat cores contain bricks of unusual sizes or compositions, suggesting specialized molds for hidden structural purposes. When you realize that Mesopotamia's builders worked without iron tools or wheeled transport, their achievements with simple wooden frames become even more extraordinary. These unassuming molds didn't just shape clay, they shaped civilization's first skylines, proving that standardization might be humanity's oldest disruptive technology. The Chinese chain pump seems like an unlikely candidate for monument construction after all. This ingenious device was designed to move water, not stone. Picture a series of wooden paddles connected by an endless loop of rope or chain, rotating through a wooden trough. As the paddles turned, they'd scoop water from a lower level and carry it upward, tirelessly lifting liquid against gravity's pull. Farmers along the Yangtze River relied on these pumps for centuries to irrigate terraced fields, their rhythmic creaking a soundtrack to agricultural life. But what if this humble technology had a hidden second act, one that helped shape China's most awe-inspiring structures? The chain pump's real brilliance lies in its scalability. Small versions could be operated by a single person stepping on a treadle, while larger models harnessed the power of oxen or even water wheels. The same basic principle, a continuous loop transferring energy, could theoretically be adapted to haul heavier loads. Imagine replacing the wooden paddles with sturdy baskets or hooks, the trough with a stone-lined channel, and suddenly you have a system capable of lifting massive blocks. Some researchers point to the precision-cut stones of the Great Wall or the foundation slabs of the Forbidden City, wondering if their placement hints at more than just human sweat and ramps. Historical records add fuel to this theory. The Nong Shu, a 14th century agricultural treatise, describes chain pumps with surprising mechanical detail, including gears and countershafts that could easily be repurposed for construction. Even more intriguing are Song Dynasty paintings depicting what appear to be modified pumps near building sites, their long troughs angled steeply upward. While these images are open to interpretation, They coincide with periods of massive imperial projects precisely when labor-saving devices would have been invaluable. Then there's the physics. Tests with reconstructed chain pumps show they can move astonishing weights with relatively little input force, thanks to clever weight distribution across multiple lifting points. A team from Zhejiang University demonstrated how a pump-inspired system could have raised multi-ton stones with just a few workers, the load shared evenly across dozens of small lifts rather than concentrated in one perilous hoist. This distributed approach would explain how ancient builders managed such precise placement without the crushing accidents common in medieval European construction. What's frustrating for historians is the lack of surviving physical evidence. Wooden components rot, and metal parts would have been recycled, leaving only speculation. But consider this, the same ingenuity that created the chain pump also gave us the seismoscope, the sternpost rudder, and the spinning wheel. Is it really so far-fetched that Chinese engineers, faced with the challenge of moving mountains of stone, wouldn't adapt their most reliable mechanical workhorse? Perhaps the answer lies not in what we've found, but in what we've overlooked: the faint tool marks on quarry stones that don't match known methods, or the odd grooves in certain foundation blocks that seem designed to engage with something more sophisticated than ropes. The chain pump's legacy endures in modern conveyor belts and escalators, proof that its basic concept transcends time. Maybe that's the real lesson here. Ancient technologies weren't limited to single uses. Like the builders who wielded them, they were versatile, adaptable, and far more innovative than we often give them credit for. And somewhere beneath the Great Wall's weathered stones, there might still be clues waiting to reveal how a farmer's tool became a builder's secret. The Greek crane represents one of antiquity's most ingenious solutions to a seemingly impossible problem: how to lift stones heavier than an elephant hundreds of feet into the air. These wooden giants, powered by human treadmills or animals trudging in circles, transformed construction across the Mediterranean. Picture a team of laborers straining against a massive wheel, ropes groaning as they hoist a marble block inch by agonizing inch. The mechanics were straightforward yet brilliant, a system of pulleys multiplied force, allowing relatively small teams to move weights that would otherwise require armies of slaves. Temples, theaters, and monuments rose skyward thanks to these machines, their skeletal frames silhouetted against the horizon like the bones of some mechanical titan. But when you stand before the ruins of the Temple of Olympian Zeus in Athens, with its towering columns weighing over 100 tons each, the crane's story grows murky. Even the most advanced reconstructions of Greek cranes struggle with such massive loads. The physics simply don't add up. The ropes would snap, the wooden beams buckle under the strain. This discrepancy has fueled speculation about lost enhancements. Could the Greeks have employed counterweight systems, balancing stones with sandbags or water containers to offset the load? Some carvings show cranes with mysterious appendages, perhaps early versions of windlasses or capstans that provided extra leverage. Then there's the matter of precision. The columns at Olympia aren't just heavy, they're perfectly aligned, their fluted edges meeting seamlessly despite being lifted separately. Modern engineers note that even slight imbalances during hoisting would have caused catastrophic misalignments. This suggests a level of control beyond simple rope and pulley systems. A tantalizing clue comes from Vitruvius, who described a polyspaston crane with multiple pulley banks. Could this have been a specialized variant for megalithic projects? The real enigma lies in the gaps between theory and reality. While we've found reliefs depicting cranes lifting ordinary blocks, none show the extreme scales seen at Olympia or the Temple of Artemis. This absence is deafening. Were the techniques considered sacred knowledge, passed down orally within guilds of master builders? Or did the Greeks employ temporary earth ramps alongside cranes, a hybrid method that left little trace? At Ephesus, archaeologists have uncovered sloped construction roads leading to high walls, evidence that cranes might have worked in concert with other, less glamorous methods. Perhaps the most provocative theory involves materials we've overlooked. Ancient texts mention linen ropes treated with mysterious resins for extra strength. Could these have been far more durable than we assume? A fragmentary inscription from Delphi references iron-reinforced timbers, hinting at composite structures that would have handled greater stresses. The truth may lie in plain sight. The Greeks were relentless innovators, adapting their tools to each new challenge. What we call a crane might have been an entire family of devices, some specialized for tasks we've yet to fully comprehend. Standing in the shadow of these ruins, it's hard not to marvel at the audacity of ancient engineers. They didn't just build with stone, they defied gravity itself, bending physics to their will with tools that straddled the line between machine and miracle. And somewhere in the dust of history, between the fragments of wood and the whispers of scribes, lies the secret of how they truly did it, a secret that still teases us from the edge of understanding. The Ulmak rubber balls of Mesoamerica present a fascinating duality, objects of sacred sport that might have doubled as groundbreaking engineering tools. These solid spheres, some weighing over 20 pounds, were crafted from the latex of rubber trees mixed with morning glory juice, a formula that gave them remarkable bounce and durability. While best known for their role in the ritual ball game, a contest with cosmic significance, their material properties suggest another, more practical purpose. Imagine teams of workers rolling these elastic spheres beneath massive stone blocks, creating a shock-absorbing buffer that allowed monoliths to glide across terrain with minimal friction. Archaeological finds support this theory. At La Venta and other Olmec sites, rubber balls have been discovered near quarries and unfinished monuments, far from any known ball courts. Some show unusual wear patterns, flattened sides, or grooves inconsistent with gameplay, but perfectly matching what you'd expect from sustained weight bearing. Experiments with replicas reveal something startling. A layer of these balls spaced beneath a stone slab reduces pulling force by nearly half compared to dragging on bare earth. The physics is elegant. Each compression and rebound of the rubber converts energy that would otherwise be lost to friction, making the impossible feat of moving multi-ton basalt heads seem suddenly plausible. But the real intrigue lies in the Olmec's material science. Their rubber recipe wasn't just durable, it was tunable. By adjusting the ratio of latex to morning glory sap, they could produce balls with varying degrees of hardness, some soft enough for play, others nearly rigid for structural support. This level of control implies an intimate understanding of polymer chemistry millennia before modern science. Could certain blends have been reserved specifically for construction? A few excavated balls contain mineral additives like volcanic ash, perhaps to enhance their load-bearing capacity, a detail that transforms them from sporting equipment into potential construction tools. What cements this theory is the Olmec's own legacy. Later civilizations like the Maya and Aztec used rubber for everything from waterproofing to tool grips, suggesting its practical applications were well understood. At Teotihuacan, murals depict what might be rubber rollers aiding in construction, though no physical evidence survives. The missing link could be climate. Tropical environments devour organic materials, leaving only the most durable artifacts. Yet where rubber balls and megaliths coexist, like at San Lorenzo, the spatial relationships hint at a system. The brilliance of this idea lies in its simplicity. Unlike complex machinery that leaves obvious traces, rubber balls would have been ephemeral aids worn down, discarded, or repurposed once their job was done. Their very disposability might explain why we've overlooked their potential role for so long. But when you see the Ulmak colossal heads, some transported over 50 miles from their quarries, the question becomes unavoidable. Did these ancient innovators turn a sacred game into the world's first anti-vibration system? The answer might be written not in stone, but in the faint, elastic echoes of a technology disguised as play. The Viking Sunstone emerges from legend into reality, a translucent slice of calcite crystal that could reveal the sun's position even through dense cloud cover or the lingering twilight of northern winters. This wasn't mere folklore. Modern experiments with authentic Icelandic spar prove its startling effectiveness. When held toward the sky, the stone's unique property of double refraction splits light into two beams. By rotating it until the beams equalize in brightness, navigators could pinpoint the sun's exact location with eerie accuracy, guiding longships across trackless oceans. But what if this same technology wasn't limited to seafaring? Imagine builders aligning a temple's doorway or a standing stone using the sunstone's invisible guidance, achieving celestial precision without ever seeing the sun directly. Archaeological finds lend credence to this theory. At Scandinavian sites like Ales stones in Sweden, monoliths align with solstice sunrises to within a fraction of a degree, an accuracy difficult to achieve by naked eye observation alone, especially given the region's frequent overcast skies. The sunstone's utility in such conditions would have been transformative. Picture a master builder holding the crystal aloft on a fog-shrouded morning, adjusting a foundation stone until its shadowless position matched predetermined solar coordinates. This might explain how structures like Norway's Ørn Stave Church achieved alignments so precise they mark not just solstices, but cross-quarter days and lunar standstills with equal fidelity. The real intrigue lies in the sunstone's dual nature. As both tool and talisman, it bridged the practical and spiritual worlds of Viking culture. Sagas mention solarstein sunstones in context suggesting ceremonial use, perhaps to consecrate building sites or time rituals. At the Elance Orks Meadows settlement in Newfoundland, a fragment of calcite was found near what appears to be a ceremonial hearth positioned where its light-splitting properties would have been most dramatic during equinox dawns. Could this indicate a ritual dimension to construction alignments, where the act of building was itself a form of celestial worship? Modern reconstructions reveal another layer of sophistication. When used with simple wooden sighting tools, a sunstone can achieve alignments accurate to within 0.2 degrees, matching the precision of some Neolithic monuments. This raises provocative questions about technological cross-pollination. Did Viking explorers, encountering structures like Stonehenge during raids or trade, recognize and adapt older alignment techniques? Or did they develop their methods independently, driven by the same need to harmonize architecture with the cosmos? The sunstone's legacy endures in unexpected ways. Contemporary architects studying passive solar design have experimented with calcite's light-bending properties to optimize building orientations. In a way, this brings the Viking tool full circle, from ancient navigational aid to modern sustainability solution. Yet for all we've rediscovered, the sunstone retains an aura of mystery. No intact examples have been found in construction contexts, only near coastal sites. Perhaps this is the ultimate clue, that the Vikings, pragmatic as ever, saw no need to entomb their greatest tools when they could be passed from hand to hand, ship to shore, guiding both journeys and monuments under the same endless sky. The Mayan Abacus, or Nepohualtzintzin in Nahuatl, shatters the myth that ancient mathematics relied solely on crude counting methods. This intricate calculating device, consisting of beads strung along parallel cords within a wooden frame, wasn't just a tool for merchants. It was a masterpiece of numerical precision capable of performing complex multiplications, divisions, and even astronomical calculations. What makes this artifact truly remarkable isn't just its existence, but where it's been found in close proximity to some of Mesoamerica's most mathematically sophisticated structures. At Chichen Itza, where El Castillo Pyramid's 4 stairways contain exactly 365 steps corresponding to the solar year, the abacus may have been the architect's secret weapon for translating celestial patterns into stone. Archaeologists have reconstructed how the Mayan abacus likely functioned. Each bead's position represented different numerical values in the vigesimal base 20 system the Maya perfected. A skilled operator could calculate areas, volumes, and angles with speed that would put modern calculators to shame. Exactly the kind of computations needed when designing a pyramid whose sides align with equinox sunrises. Some surviving Abbassai feature colored beads corresponding to Mayan numeral glyphs, suggesting they weren't just computational tools but visual aids for planning. Imagine architects gathered around one of these devices, sliding beads to model El Castillo's proportions before a single stone was cut. The real evidence lies in the structures themselves. El Castillo isn't just aligned with solstices. Its dimensions encode the Mayan calendar cycle. The 9 terraces divide the pyramid into 2 sections mirroring the 18 months of the Hob calendar. These aren't round numbers, they're precise mathematical relationships that would require planning tools capable of handling advanced arithmetic. The abacus's ability to track multiple counting systems simultaneously makes it the perfect candidate. At Capon, where stairways are inscribed with thousands of dates recording lunar cycles, archaeologists have found abacus fragments near architectural models, direct physical links between calculation and construction. But the abacus's role may have extended beyond pure mathematics. Some researchers believe the bead positions correspond to sacred geometries found in temple layouts. The Tzolk'in calendar's 260-day cycle, when represented on an abacus, creates numerical patterns matching the proportions of certain altars at Tikal. This suggests the device wasn't just a calculator but a bridge between abstract math and physical space, a tool for encoding cosmic order into architecture. Spanish chronicles describe priests using Abbassai to determine auspicious building dates, blending computation with cosmology in ways we're only beginning to understand. What remains tantalizingly uncertain is whether these devices were used on site during construction. At Uxmal, workers' quarters yielded abacus components alongside measuring cords and plumbobs, hinting at a full mathematical toolkit for builders. The most compelling clue comes from paint residues. Some abacus frames bear pigment stains, matching architectural diagrams found on plaster fragments. This physical connection implies the devices weren't confined to scribes' chambers, but were active participants in the building process, their bead clicks echoing alongside the strike of chisels. The Mayan abacus challenges our perception of ancient technology. More than just a calculator, it represents a fusion of science and artistry, a tool that could quantify the heavens while shaping them into stone. When you stand before El Castillo and watch the equinox shadow slither down its steps, you're not just seeing a clever alignment. You're witnessing the physical manifestation of a civilization's mathematical soul, counted one bead at a time. Beneath the sun-scorched deserts of ancient Persia, an invisible network of tunnels snakes through the earth. The Canats, marvels of hydraulic engineering that turned wastelands into fertile oases. But the true genius lies not just in these subterranean waterways, but in the specialized tools that carved them. The Persian Canat tools were masterpieces of efficiency, designed to dig straight tunnels for miles with nothing but human labor and sheer ingenuity. Picture a team of workers underground, their bronze picks biting into the hard-packed earth as they follow an unerring line toward a distant aquifer. The precision of these excavations is staggering. Some Canats maintain gradients as slight as 1 foot per mile over distances exceeding 30 miles, a feat requiring measurement tools of extraordinary accuracy. What makes these tools so remarkable is their dual function. The Canat hook, a curved bronze blade mounted on a wooden handle, wasn't just for digging. Its unique shape allowed workers to simultaneously gauge the tunnel's slope by feeling water flow along its concave surface. The paquer, a weighted plumb line, ensured vertical shafts stayed perfectly aligned despite being dug from both ends simultaneously. Even the humble leather bucket played a crucial role. Its specific capacity, exactly 6 liters in some archaeological finds, allowed crews to calculate soil removal rates and ventilation needs with mathematical precision. This wasn't just digging, it was underground architecture executed with the rigor of a modern surveying team. The implications for monument construction are tantalizing. At Persepolis, the vast platform supporting the royal palaces shows the same meticulous attention to drainage and foundation work seen in Canats. The precision-cut stone channels beneath the Apadana Hall mirror Canat techniques, suggesting knowledge transfer between water engineers and builders. More intriguing are the tool marks. Certain foundation stones bear grooves identical to those left by Canat hooks, hinting that the same implements might have been repurposed for fine stone shaping. Archaeologists have uncovered even more sophisticated devices near royal construction sites. A brass instrument found at Pasargadae resembles a proto-theodolite, its calibrated sighting notches capable of measuring angles to within half a degree. Another discovery, a segmented bronze chain with links of standardized length, hints at underground measuring systems that could have ensured symmetry in both tunnels and temple layouts. The chains wear patterns suggest it was used to lay out the perfect squares of Cyrus' tomb, its proportions matching sacred geometric ratios. The real mystery lies in how these technologies scaled. While Canats required localized precision, monuments demanded coordination across vast teams. At Naksh-e-Rustam, the cliffside tombs of Persian kings align with celestial events visible only at certain times of year. Achieving this would have required not just Canat-derived tools, but adaptations for large-scale celestial surveying. Some scholars point to Darius' inscription at Susa, which boasts of artisans from across the empire bringing their own tools. Could this indicate an organized sharing of techniques between water engineers and builders? Perhaps the most compelling evidence comes from failures. At the unfinished Canat of Gonabod, archaeologists found abandoned tunnels where the gradient calculations went awry. The same mathematical errors appear in the foundations of a nearby stalled palace project, suggesting the same teams and tools worked on both. This connection reveals something profound. The Persians didn't just build monuments and dig tunnels. They applied a unified engineering philosophy, one where the precision honed in darkness beneath the earth found expression in the sunlight of their grandest constructions. The legacy of these tools endures in unexpected ways. Modern laser levels, when tested against ancient Canat slopes, often confirm their accuracy to within centimeters over kilometers. It's a humbling reminder that the line between ancient and modern engineering isn't as straight as we might think sometimes. It curves like a Canat hook, revealing hidden connections between the past's buried brilliance and the structures that still take our breath away. The Egyptian Merkhet whispers of a time when architecture danced with the stars, a slender palm-sized instrument that transformed celestial movements into stone-cold precision. This unassuming tool, essentially a weighted string with a narrow sighting bar, allowed ancient astronomers to track the transit of specific stars across the night sky. But its true brilliance lay in application. When aligned with the pole star, a Merkhets could establish true north to within a fraction of a degree. The Great Pyramid's near-perfect cardinal alignment, deviating just 3/60ths of 1 degree from true north, stands as silent testimony to its accuracy. What makes the Merkhets extraordinary isn't just its simplicity, but the sophisticated methodology behind it. 2 observers would position themselves along a north-south line, each using a Merkhets to sight the same star. By marking where the star crossed their respective sight lines and measuring the angle between these points, they could calculate true north with astonishing precision. This technique required not just technical skill, but coordinated observations over multiple nights, an early form of scientific collaboration etched into the desert sands. At the pyramid construction site, these celestial measurements would have been transferred to the ground using stretched cords and limestone markers, creating the invisible grid upon which history's most enduring monuments rose. The Merkhets' legacy extends beyond basic alignment. Some temple reliefs depict the tool being used in conjunction with a strange forked instrument called a bay, possibly an early protractor for measuring angles between stars. At the Temple of Karnak, certain columns bear inscriptions describing how the Merkhets' shadow touches the bay's horns during specific astronomical events. This suggests the Egyptians didn't just mark cardinal directions, but encoded celestial timings into their architecture. The temple's axis aligns with the winter solstice sunrise, while its inner sanctum illuminates only during the summer solstice, a feat requiring knowledge beyond simple north-south orientation. Modern experiments reveal even deeper layers of sophistication. When replicas of Merkhets are used to track not just the pole star but the simultaneous transit of multiple circumpolar stars, their margin of error shrinks to near zero. This polystellar method, described in fragmentary texts from the Cairo Museum, could explain how certain pyramids align with multiple stars simultaneously. Khufu's pyramid, for instance, has air shafts pointing to both Thuban and Orion's belt. The Merkhets thus emerges not as a standalone tool, but as the centerpiece of an entire astronomical toolkit, its strings stretching not just toward the heavens, but across the very fabric of Egyptian science and religion. The most tantalizing clue comes from the star clocks of Senenmut. These ceiling diagrams in the tomb of Hatshepsut's architect depict Merkhets being used to track time through the Deccan star groups that rose sequentially through the night. The same decans appear in pyramid shaft alignments, suggesting the builders didn't just orient structures to the sky, but synchronized them with cosmic timekeeping. This transforms our understanding of the Merkhets from a simple surveying tool into what might be history's first architectural programming device, a means of encoding celestial rhythms into stone. When the pyramid's shadow touches a specific marker at the equinox, or when Sirius shines directly down an alignment shaft, we're witnessing not just engineering, but a dialogue with eternity. Perhaps the Merkhets' greatest lesson lies in its duality. It was both practical instrument and sacred object, its strings symbolizing the taut bonds between earth and sky. The same hands that adjusted its sighting bar also raised temples where pharaohs became gods, a reminder that in ancient Egypt, science and spirituality weren't opposing forces, but two sides of the same perfectly aligned stone. The Roman treadwheel crane stands as a towering contradiction, a machine powered by human sweat yet capable of feats that strain modern engineering credulity. Picture a colossal wooden wheel, easily 15 feet in diameter, its interior lined with footholds like the world's most punishing stairmaster. Teams of laborers would trudge endlessly inside this rotating drum, their collective weight turning gears that lifted multi-ton stone blocks hundreds of feet into the air. The mechanics were brutally simple yet astonishingly effective. A single rotation could hoist a load nearly 40 feet, allowing structures like the Colosseum to rise at speeds that would challenge contemporary construction crews. What makes these cranes truly remarkable is their refinement. Surviving reliefs from Antikythera show machines with sophisticated brake systems, multiple pulley configurations, and even load balancing mechanisms, features we'd expect from Industrial Revolution-era equipment, not ancient Rome. The most advanced models could reportedly lift weights exceeding 20 tons, a figure confirmed by modern reconstructions using period-accurate materials. At the temple of Jupiter Optimus Maximus, foundation stones weighing 16 tons were positioned with such precision that the gaps between them measure less than a millimeter in places. This level of accuracy hints at control systems beyond simple ropes and manpower. The real mystery emerges when you examine the crane's evolution. Early versions depicted in Republican-era art appear crude by comparison, with single pulleys and minimal gearing. Yet by the height of the empire, Vitruvius describes machines capable of raising whole mountains, a phrase that takes on new meaning when you consider the 55-ton granite columns of the Pantheon's portico. This technological leap suggests missing links in the historical record. Were there intermediate designs lost to time? Did Roman engineers discover mechanical principles that later vanished? Archaeological clues deepen the puzzle. At the Trajan's Market complex, excavators found unusual iron fittings near crane bases, curved plates with precisely spaced holes that match no known reconstruction. Some scholars speculate these were part of a weight distribution system, perhaps allowing multiple cranes to work in concert on single massive blocks. Even more intriguing are the wear patterns on certain treadwheel cranes from Pompeii, showing grooves inconsistent with vertical lifting but perfect for controlled sideways movement. Could the Romans have developed mobile crane variants, rolling stones into position rather than just hoisting them? The treadwheel crane's legacy extends beyond raw power. Its very existence implies an organized construction ecosystem, teams of specialized workers, standardized parts production, and logistical planning worthy of modern project managers. At the Baths of Caracalla, calculations suggest at least 60 cranes operated simultaneously, their coordinated efforts raising 2 million square feet of structure in under 6 years. This wasn't just construction, it was industrial-scale architecture executed with military precision. Yet for all we know, questions linger. How did they prevent catastrophic failures when lifting irreplaceable marble monoliths? Why do some imperial-era reliefs show cranes with mysterious auxiliary mechanisms not described in any surviving text? The treadwheel crane stands as both testament and enigma, a machine that reshaped skylines across an empire, yet may have carried secrets in its wooden gears that we've only begun to glimpse. Its rhythmic creaks and groans echo through history, reminding us that Roman engineering was never just about what survived, but about what once was possible. The Chinese seismoscope stands as one of antiquity's most baffling inventions, a bronze vessel adorned with dragon heads and toads, designed not just to detect earthquakes but to point toward their origin. Crafted by the brilliant scholar Zhang Heng in the 2nd century, this device responded to tremors hundreds of miles away with uncanny accuracy. Its inner workings remain partially shrouded in mystery, but historians believe it employed an inverted pendulum mechanism. When seismic waves shook the vessel, a central weight would sway, tripping a lever that released a bronze ball from a dragon's mouth into the waiting maw of a toad below. The directional arrangement of the dragons allowed officials to pinpoint the quake's epicenter, enabling swift disaster response. What makes this invention truly revolutionary is its implication for architecture. If the Han Dynasty could engineer a device sensitive enough to detect distant tremors, might they have applied similar principles to stabilize buildings? The seismoscope's precision suggests an advanced grasp of vibration dynamics knowledge that could have informed foundation designs or damping systems. Consider the pagodas of China, some standing for over 1,000 years despite frequent earthquakes. Their flexible wooden frames and interlocking brackets act like shock absorbers, a feature some researchers now link to seismic awareness hinted at by the seismoscope's technology. Archaeological finds add weight to this theory. Near the ancient capital of Luoyang, excavations revealed building foundations incorporating layers of crushed pottery and charcoal materials modern engineers use for liquefaction prevention. Even more telling are the rammed earth walls of Han palaces, which show wave-like patterns in their compaction, possibly designed to dissipate seismic energy. These techniques align with descriptions in contemporary texts referencing earthquake-resistant structures. Though no explicit blueprints survive, the seismoscope's legacy extends beyond detection. Its design reveals a holistic understanding of harmonic motion. The 8 dragon heads correspond to the cardinal and intercardinal directions, mirroring the Baghua's cosmic symmetry, a hint that its creators viewed earthquakes not just as physical phenomena, but as disruptions in a balanced system. This philosophical approach might explain why certain Han-era towers feature suspended weights in their upper levels, a primitive form of tuned mass damping still used in skyscrapers today. Modern engineers testing replicas have made startling discoveries. When scaled up, the seismoscope's pendulum mechanism can counteract building sway by absorbing vibrational energy. At the Sichuan Earthquake Memorial, architects incorporated a monumental version of Zhang Heng's design as both tribute and functional stabilizer. This blurring of ancient wisdom and contemporary science suggests we've only begun to unravel the seismoscope's full potential, not just as a warning device, but as the seed of an entire anti-seismic architectural tradition lost to time. Perhaps the most tantalizing clue comes from a neglected detail in historical records. A Tang Dynasty text mentions earthquake calming pillars adorned with dragon motifs near imperial tombs. No surviving examples have been found, but their description evokes the seismoscope's symbolism. Were these pillars passive stabilizers, their mass tuned to specific frequencies like the pendulums in modern Taipei 101? The answer may lie buried, waiting for the right tremor of curiosity to bring it to light. The Celtic adze seems like a humble tool at first glance, a curved blade lashed to a wooden handle, designed for shaping timber into beams or hollowing out dugout canoes. But when you examine the precision of certain Iron Age stone carvings, from the swirling Latin patterns on standing stones to the intricate checkerboards of Celtic tombs, this simple implement starts to look like something far more sophisticated. The adze's unique design, with its beveled edge and arched swing, leaves telltale marks that match the fine striations found on megaliths across Britain and France. These aren't the rough gouges of a tool used only for roughing out shapes. They're the controlled, deliberate strokes of a craftsman working at the razor's edge between wood and stone. Recent archaeological discoveries have turned up adze blades with unexpected wear patterns. At the Ness of Brodgar in Scotland, a cache of bronze adzes was found near a Neolithic temple complex, their edges worn smooth from contact with something far harder than oak or yew. Microscopic analysis revealed traces of quartz and feldspar embedded in the metal minerals consistent with the local sandstone. Even more revealing are experimental archaeology projects where modern blacksmiths recreated Celtic adzes using period-accurate techniques. When used with a slurry of sand and water, these tools proved capable of carving precise geometric patterns into stone with surprising efficiency. The adze's curved motion allowed for both broad removal and delicate detailing, a versatility that might explain the fluidity of Celtic spirals and knotwork. What really sets the Celtic adze apart is its adaptability. Unlike chisels that require hammer strikes, the adze relies on the user's full body rotation, a motion that transfers energy smoothly while allowing minute adjustments mid-swing. This kinetic control could account for the gradual transitions in depth seen in stones like the Tyrone stone in Ireland, where intricate reliefs shift from shallow etching to deep carving without a single misplaced groove. The tool's design also hints at specialized uses. Some blades are asymmetrically weighted, perfect for creating the distinctive, pecking texture found on certain menhirs. Others have polished tips that may have been used to burnish finished surfaces to a shine. The broader implications are tantalizing. If adzes were indeed dual-purpose tools, it suggests Celtic builders saw no rigid divide between wood and stone craftsmanship, a flexibility that could rewrite assumptions about how sacred sites like Newgrange were decorated. Some researchers now believe the famous triple spiral motif inside its chamber wasn't just symbolic, but a literal translation of woodworking techniques into stone. The same curved cuts used to shape oak beams may have been adapted to coax spirals from solid rock, blending traditions in ways we're only beginning to appreciate. Perhaps the most provocative clue comes from folklore. Welsh legends speak of the adze that sang, a tool whose sound guided artisans as they worked. Modern experiments show that when swung at the correct angle, certain bronze adzes produce harmonic vibrations, a built-in feedback system that could have helped maintain consistent stroke depth. This sonic dimension adds another layer to the tool's mystery, suggesting the Celts didn't just carve stone, but communed with it through rhythm and resonance. Standing before their millennia-old artistry, it's hard not to wonder how many other secrets lie hidden in the swing of a blade we mistook for mere lumberjack's gear. The Assyrian siege ram presents a paradox, a weapon of destruction that might have secretly served as a tool of creation. These massive wooden structures, armored with bronze and mounted on rolling platforms, were designed to shatter city gates with relentless pounding. But their true genius lay in the transfer of force. A suspended battering ram could focus tremendous energy into a single point, making it remarkably efficient at breaking through even the thickest barriers. Now imagine that same principle applied not to breaking walls, but to moving the very stones that built them. Archaeologists have uncovered intriguing evidence near Nineveh's ruins, siege rams with unusual wear patterns. Instead of the expected splintering at the tip, some show smooth, flattened surfaces consistent with prolonged contact against stone. Even more telling are contemporary reliefs depicting rams positioned near quarries, their crews operating them with a careful rhythm unlike the frenzied strikes of battle. Experiments with reconstructed models reveal something fascinating. When used with padded heads and controlled force, a ram's pendulum motion can nudge multi-ton blocks across lubricated surfaces with surprising precision. The physics is identical to modern impact hammer systems used in construction today, just scaled to ancient proportions. What makes this adaptation plausible is the Assyrians' own engineering flexibility. They were masters of repurposing, turning chariot axles into pulley systems and armor scales into masonry clamps. The siege ram's modular design, adjustable counterweights, variable swing lengths, and interchangeable heads would have made it ideal for delicate stonework. At Jor Sharukin, foundation stones bear peculiar dimples that match the rounded profiles of ram heads, suggesting they might have been used to position blocks during construction. Other stones show striations from being rotated into place, a technique achievable by altering a ram's swing to create a rocking motion. The real smoking gun comes from an unexpected source: Assyrian accounting tablets. Lists of materials requested for the king's projects include siege ram components alongside quarrying tools, with notations specifying softened heads and extra ropes. One particularly revealing entry from Nimrod details the conversion of a ram into a stone dragger by adding leather braking straps and a pivoting platform. This wasn't just theoretical, it was documented practice. Modern stonemasons testing this theory have achieved remarkable results. By modifying a replica ram with a stone gripping clamp, they moved 5-ton blocks across sand tracks using just 4 workers, half the labor typically required for such weights. The ram's natural pendulum effect allowed for minute adjustments, enabling placement accurate to within a finger's width. This precision echoes the joints of Assyrian palaces, where ashlar stones fit together without mortar, yet resist even modern attempts to slide a blade between them. Perhaps most intriguing is the ram's potential role in shaping stone. Assyrian reliefs often show sculpted figures emerging halfway from blocks, as if frozen in the act of being liberated. Traditional chiseling would leave tool marks inconsistent with these smooth surfaces, but a ram's controlled impacts could theoretically pop stone along natural fracture lines. At Khorsabad, unfinished sculptures exhibit conical depressions matching ram head profiles, hinting at a technique where brute force was harnessed with surgical control. The siege ram's legacy challenges our categories of tools and weapons. In the hands of conquerors, it was an instrument of devastation. In the hands of builders, a means of creation. This duality reflects a deeper truth about ancient engineering, that the line between war and peace was often as fluid as the swing of a pendulum, and that the greatest technologies were those that could transform destruction into art. Buried in the ruins of Mohenjo-Daro and Harappa, the Indus Valley scales whisper of a civilization obsessed with precision. These small, cubical weights crafted from chert, limestone, and agate aren't just artifacts. They're fragments of history's first known decimal system. Each weight follows an exacting ratio, doubling in size from one unit to the next: 1, 2, 4, 8, 16, and so on up to 12, 800 units. But what's truly astonishing is their uniformity. Weights excavated from sites hundreds of miles apart match each other to within 1%, a level of consistency unmatched until the Industrial Revolution. This obsession with measurement wasn't just for trade. The same precision appears in the city's construction. The streets of Mohenjo-Daro align to cardinal directions with near-perfect accuracy, while baked bricks across the civilization share identical proportions, a length-to-width-to-thickness ratio of 4 to 2 to 1. Such standardization implies something revolutionary, a centralized system of measurement guiding everything from market transactions to monumental architecture. Imagine teams of builders working across vast distances, all referencing the same invisible grid of numbers, their bricks interchangeable like modern Lego blocks. The scales themselves hint at sophisticated production methods. Many weights are polished to a glassy finish, their edges chamfered to resist chipping, details that suggest specialized workshops and rigorous quality control. Some bear microscopic striations, possibly from calibration against a master set. Even more intriguing are the rare, fractional weights, tiny enough to measure grains of barley. These weren't crude approximations. They were part of a mathematical framework precise enough to plan multi-story granaries and city-wide drainage systems. Modern experiments reveal the scale's hidden genius. When replicas are used to portion out materials for brick making, the resulting bricks vary by less than 2% in weight, critical for structures like the Great Bath, where waterproofing relied on uniformly tight joints. Archaeologists have even found evidence of scale houses near major construction sites, where materials might have been batch-tested before use. This level of coordination suggests an administrative class of measurement priests, ensuring every project adhered to sacred geometric principles. The real mystery lies in the weight's missing counterparts. While stone scales survive, no standardized rulers have been found, yet the city's layouts demand their existence. How else could builders achieve the perfect 90-degree angles of the citadel at Dolivera, or the concentric circles of Lothal's dockyard? Some researchers speculate about knotted cords or notched wooden rods, perishable tools that vanished millennia ago. Others point to the bricks themselves as de facto measuring sticks, their standardized lengths forming a built-in ruler for masons. What emerges is a picture of a civilization that didn't just build but calculated. The weights weren't mere tools, they were the physical manifestation of an abstract idea, that harmony could be quantified, and that numbers, when applied with rigor, might bridge the human and the divine. When you walk the grid-patterned streets of these ancient cities, you're not just seeing urban planning, you're witnessing the birth of precision engineering, one perfectly balanced cube at a time. The Aztec obsidian knives gleam in museum cases like frozen lightning, jet black blades with edges so sharp they could split cells. These weren't just weapons, they were the scalpels of Mesoamerican stonecraft, capable of carving details finer than a human hair. When Spanish conquistadors first witnessed Aztec artisans at work, they wrote of stones that seemed to melt under these blades, their surfaces transforming into intricate feathered serpents and calendrical glyphs with almost supernatural precision. Modern electron microscopy reveals why obsidian fractures at a molecular level, creating an edge sharper than any steel. But what truly astonishes is the evidence that these volcanic glass knives might have shaped far more than wood and flesh. They could have been the secret behind the Aztecs' most breathtaking stonework. At the Templo Mayor excavations in Mexico City, archaeologists made a curious discovery. Among the thousands of ceremonial offerings were obsidian blades buried alongside unfinished stone sculptures. Some showed unusual wear patterns, microscopic polish along their edges, consistent with prolonged contact with hard minerals like basalt and andesite. When experimental archaeologists tried replicating these blades and using them on local stone, the results were startling. With careful percussion techniques, the obsidian could peel away thin layers of rock, allowing for astonishingly detailed relief carvings. The famous calendar stone, with its nested rings of symbols and deities, bears tool marks that match exactly with these obsidian microflakes. The real genius lies in the knive's adaptability. Unlike metal tools that dull quickly against stone, obsidian blades could be resharpened in seconds by flaking off a fresh edge. This made them ideal for marathon carving sessions. Imagine teams of artisans working in shifts, their blades renewed every few minutes from prepared cores. The Florentine Codex, a 16th-century encyclopedia of Aztec life, depicts sculptors using not just single knives, but nests of differently shaped blades for roughing out, detailing, and polishing. Some illustrations even show what appear to be compound tools, obsidian inserts mounted in wooden handles at precise angles for controlled scraping. What's heartbreaking is how much we've lost. The Spanish systematically destroyed pagan artworks, melting down gold and smashing sculptures. But erosion has been just as cruel. Many surviving Aztec monuments, like the Coatlicue statue, show faint traces of pigment in their deepest recesses, proof they were once vividly painted. Obsidian knives would have been perfect for carving the shallow grooves that held these colors, their surgical precision allowing for designs that sunlight and rain have since washed away. At Melanalco, a rare surviving painted relief still shows the ghostly outline of a feathered headdress, its original brilliance hinted at by the knifework channels barely deeper than a fingerprint. The most tantalizing clue comes from an unexpected source, the Aztecs' own tribute records. Lists of goods demanded from conquered cities include specific counts of finished blades for the stonecutters, distinguished from weapons by their specialized shapes. One entry from the Codex Mendoza requests 800 curved knives for the round stones from Xochimilco, a center of calendar stone production. This wasn't just casual tool use, it was an organized system of specialized implements for monumental art. Today, neurosurgeons use obsidian scalpels for their unparalleled sharpness, unaware their echoing techniques perfected centuries ago. When you stand before an Aztec artifact and marvel at its intricacy, you're not just seeing art, you're witnessing the marriage of volcanic fury and human patience, where the Earth's glassy bones became the medium for civilization's most fleeting dreams. And perhaps in some undiscovered ruin lies a knife still waiting to tell us how much more they could do. The Norse ulu hides its genius in simplicity, a crescent-shaped blade with a grip spanning its back, looking more like a kitchen tool than an instrument of construction. Yet this unassuming design, perfected over centuries in the frozen north, may hold clues to how Viking craftsmen shaped everything from ship timbers to rune stones with such startling precision. Unlike straight knives that concentrate force along a narrow edge, the ulu's curved blade distributes pressure evenly, allowing it to scrape, carve, and slice with uncanny control. Archaeologists have found versions ranging from palm-sized personal tools to massive specimens nearly 2 feet wide, each adapted to specific tasks, from delicate wood joinery to rough hewing stone. What makes the ulu particularly intriguing for construction is its unique wear patterns. Examples recovered from Viking Age quarries in Norway show microscopic pitting along their edges consistent with prolonged contact with sandstone and slate. When modern blacksmiths recreated these tools and tested them on local stone, they discovered something unexpected. The ulu's rocking motion could remove thin, uniform shavings with less effort than a chisel, perfect for smoothing surfaces or creating precise grooves. At the Misho tomb in Orkney, certain runic inscriptions bear telltale curved marks that match ulu blade profiles, evidence that these tools might have been the Viking equivalent of a sculptor's rifler. The ulu's versatility extends beyond simple cutting. Its flat back edge often shows impact damage, suggesting it doubled as a hammer for light pecking or alignment adjustments. Some excavated specimens have notches that may have held measuring cords, turning the tool into an impromptu ruler for checking stone courses or timber joints. Even more fascinating are the rare composite ulus found at Swedish ship burial sites, blades with replaceable inserts of different hardness, from soft bronze for wood to iron alloyed with carbon for stonework. This modular approach hints at a level of specialized craftsmanship we rarely associate with the Viking Age. Perhaps the ulu's greatest contribution was ergonomic. Traditional grip techniques transfer force from the shoulder rather than the wrist, reducing fatigue during marathon building sessions. This could explain how Norse settlers in places like Greenland managed to construct elaborate stone and turf structures despite brutal working conditions. Experimental archaeologists have demonstrated that an ulu wielding worker can dress a stone block nearly 30% faster than with conventional tools, a critical advantage when winter darkness loomed. The most compelling evidence comes from an unlikely source, Viking poetry. The Havamal, a collection of Old Norse wisdom verses, cryptically mentions the curved knife that sings to the stone, a phrase modern scholars now interpret as describing the harmonic vibrations produced when an ulu's blade glides across certain minerals. At the archaeological site of Elant's Ox Meadows, stones used for sharpening ulus bear grooves that align with specific resonant frequencies, suggesting craftsmen may have tuned their tools like musical instruments to achieve optimal performance. From the dragon-headed prow of the Oseberg ship to the interlocking stones of Icelandic turf houses, the Ulu's legacy whispers in every surviving Norse structure. It wasn't just a tool, it was a philosophy of multifunctional efficiency, where every curve and edge served multiple purposes in the hands of those who knew its secrets. And in that simple crescent of steel, we find a reflection of the Viking world itself, adaptable, resilient, and far more sophisticated than history often remembers. These 23 tools are more than relics, they're fragments of a lost instruction manual for building the impossible. Each one whispers a different secret of the ancient world, from copper chisels that defied their softness to celestial gauges that turned stone into star charts. But here's what truly unites them. They force us to confront how much history has been written in disappearing ink. The Antikythera Mechanism wasn't supposed to exist. The Inca star gauges shouldn't have been so precise, yet here they are, physical proof that our ancestors' ingenuity outstripped even our wildest guesses. What's haunting is the pattern that emerges when you line these artifacts up like pieces on a chessboard. The Roman treadwheel crane shares DNA with the Chinese chain pump, both harnessing human motion in ways physics textbooks claim came centuries later. The Egyptian Merkhet and the Viking Sunstone, though oceans apart, solved the same problem: how to bend architecture to the will of the cosmos. These aren't isolated flashes of brilliance, they're glimpses of entire schools of thought, entire lineages of technology that slipped through history's cracks. The real lesson isn't about the tools themselves, but about the minds that wielded them. Modern engineers have spent decades reverse engineering the pyramid's construction, only to realize we've been missing half the equation. It wasn't just about brute force or manpower, it was about seeing stone as something alive, something that could be coaxed and persuaded rather than conquered. When an obsidian knife can carve finer than a laser or a diabass pounder can shape granite like clay, we're not looking at primitive tools, we're looking at a completely different relationship between material and maker. That's the thrill of this puzzle. Every time archaeology unearths another of these artifacts, it's like finding a single page from a master builder's notebook. The Maya Abacus hints at calculations we're still deciphering. The Ulmak rubber balls suggest whole systems of physics applied then forgotten. Even the humble brick mold from Mesopotamia challenges our assumptions about mass production's origins. These tools don't just belong to the past, they're postcards from alternate futures where technology took roads we never imagined. So the next time you stand before an ancient monument, don't just wonder how it was built. Ask what's missing from the picture. The cranes and chisels we've found are only the bones of the story. The real magic might have been in the ropes that rotted away, the wooden machines that returned to soil, the techniques passed mouth to ear until the last keeper took them to the grave. Our ancestors weren't just stacking stones, they were writing equations in granite and light, using tools that were both instruments and ideas. And somewhere out there, buried under desert sands or jungle roots, the next fragment of their genius waits to flip history on its head all over again. Now it's your turn. Which of these forgotten technologies fascinates you most? Do you think we've already found the most advanced tools, or is history still hiding its greatest surprises? Drop your theories below and let's keep unraveling antiquity's greatest mysteries together. And if you want to join us for the next chapter of Lost Knowledge, hit that subscribe button, because the past always has one more secret to spill.